And our first speaker for today, Jos Kistemaker from the University of Queensland, to speak about the introduction to synthetic molecular motors. So when you're ready, please go ahead.
Thanks for that. Yes, currently I'm working as a DECRA postdoctoral fellow in the group of Professor Paul Byrne at the University of Queensland. But the work I'll be presenting you today has all been done at the University of Groningen under the supervision of Professor Ben Veringa. And I'd like to introduce you all into the wonderful world of synthetic molecular motors. So let's see if you can follow the slides around. There we go. A motor is actually a very broad description, and many things can be called a motor. So we can narrow it down a bit by calling it the initial source of motive power designed to drive machinery. And just that it's designed doesn't mean yet that it actually has to drive machinery directly. It's just the design part that we're most interested in. And a motor can be characterized by several features, and type of motion and dimensions speak for itself. Turnover could be a tricky one. We're all very used to regular combustion engines, for example, and we expect many turnovers. But when you have to make synthetic systems, then it does become important, because if you, for example, would have a stepper motor and it would only do a quarter turn, you can't really call it a motor if after a quarter turn it would die and never rotate again. So you need some form of repetitive motion for it to be a proper motor. There are many types of fuel you can use. There are a few examples here, but there are many more. And what's very important for a motor is that there is some form of directionality. If there's no directionality at the molecular scale, you would have just Brownian motion, and in our macro world, we're also used, you need some form of directionality to make your motor do something. And the source that controls this directionality can be either built into the motor, or an operator can direct the motor in a certain direction. And then we get to autonomy, and that's whether the motor can control its fuel use and its directionality itself, or that it is all coming from an operator. So let's go through some examples to get you ready. So two well-known examples, four-stroke combustion engine on the left, and on the right you see kinesin. And these are translational motors, one big, one small. They both function really well, can do many strokes over a lifetime, travel a far distance for their own size. They both use a chemical fuel, but where they differ is how autonomous they are. So with kinesin, as long as you provide it with ATP, it will keep walking till the end of the track. And it will decide the direction by itself based on charges built into the microtubule. Whereas with a combustion engine, a lot of smart systems had to be built in, because by itself, it doesn't really know what to do. If you just flood it with fuel, it won't work. It needs its fuel in specific intervals provided to it. And then also it doesn't start by itself. It needs a starter engine for that to determine which direction it rotates. But we're more interested in rotational engines. So let's look at two well-known examples of that. So on the left, we have an electric engine, and on the right, we see ATP synthase. One runs on electricity, the other on a proton gradient, although you can make it run the other way around by providing ATP to it. Very efficient, they can spin at thousands RPM. One uses Fleming's left-hand rule to determine which way it rotates. And of course, you can alternate this by changing the flow of electrons, but still it's built into the design whether it rotates left or right-handed. And of course, chirality is the dominant factor in which way ATP synthase rotates, because it's all the way down to the amino acids, as well in the supramolecular structure. And that brings us to synthetic rotary molecular motors. These are two nice examples from the past. These are both rotational synthetic. On the left-hand side, you see one from the Lee group. David Lee is a fantastic presenter. If you ever have a chance to see him, you definitely should. He actually uses magic during his presentations. It's a delight. And what you see there is a catenane, which practically is a rotaxane of which the ends are brought together. And there is a ring that can travel over the different stations. And to bring it from one station to another, every time a sequence of chemical reactions have to be performed. On the right-hand side, you see a motor that we developed in our group, and I want to point to specific things myself. So let me do this. There we go. So we can change the palladium source to direct whether we want to have a oxidative addition of the palladium into the carbon-bromine bond, or whether we want to have a CH insertion. And it's the sulfur, which is chiral, which directs the rotation there. But both of these examples take a long time to undergo a full rotation. So if you work really hard, in 24 hours, you can make both of these do one rotation. And that's not really what we want. We want to have much more efficient molecular motors. And that brings us to the typical Feringa motors. So in Dutch, it's pronounced Feringa, but most English speakers say Feringa. And here we see the Feringa motors. So what do we have? We have light-driven, synthetic, rotary molecular motors. Of course, they're rotational at the nanoscale. The fastest can rotate at 1 million times per minute. They're light-driven. It's chirality that direct their rotation, and they're fully autonomous. So as long as you provide them with fuel, which is light, they will rotate, and they know which direction they have to rotate in. There are 3 generations of molecular motors, and they are distinguished by where they get their chirality from. So the first thing that was developed was the first generation, logically, and they had 2 stereogenic centers. But later on, we discovered that you can have a motor functioning with just a single stereogenic center. And that lower half there, which is a fluorine moiety, I don't know, is this a pointer? I'm trying to point to it, but this shows up. This lower half, this fluorine, is symmetric, and therefore it doesn't have any chirality, but there's still 1 stereogenic center in the upper half. And then finally, we've developed these molecular motors, which have a mirror plane in the middle, and any molecule with a mirror plane becomes achiral, and still they manage to be unidirectional. We'll get to them in the end. But first, let's look at how molecular motors work. Somebody needs to mute there. Thank you. Okay. In the top, we see the 2 enantiomers. Like I said, this is we're using a 2nd generation molecular motor as an example. So there's only a single stereogenic center, and as a stereogenic center, you have a mirror image of that. So we have the S and R enantiomers here. But that's not the only chiral information in this molecule, because it's an overcrowded alkene, and an overcrowded alkene is named such because they're so big they can't stay flat anymore. An alkene wants to be flat, but these can't. And that makes them helical. And if we look at the top-down view, which you see left and right, you see that there is a helical sense to these molecules. And they get designators M and P, minus and plus, which means a left-handed or a right-handed helix. So if we take this left-handed helix and we look at it from the side. So here we're at the bottom, we're looking at it from the side. We see the proton in red and the methyl group in yellow. And as you can see in the stable form, that is what you get after you synthesize these molecules, you see that the xylene moiety in the back, the big aromatic group, and the methyl are on the same side of the fluorine lower half. It's happy that way. However, the xylene moiety could move over the lower half to the other side, which you see on the right-hand side. And here, there's quite a lot of steric hindrance. And because of that steric hindrance, this molecule is not happy, it's a higher energy, so it's metastable. And these 2 molecules are diastereoisomers of each other, because even though they have the same stereogenic center, their helicity is different. So on the left-hand side, we have a left-handed helicity, M, and on the right-hand side, we have a right-handed helicity, P. So if you ever were to generate this molecule, it would very happily, thermally, through what we call a thermal helix inversion, revert back to its stable isomer. So how could we generate such a molecule? Well, that's where light comes in. At the top, we see the stable molecule being happy, but then when we irradiate it with UV light, it can undergo a photochemical EZ isomerization. After photochemical EZ isomerization, the upper half flips with respect to the lower half. And that's the easiest way for it to rotate because it involves the least amount of steric hindrance. But the molecule it ends up in is sterically hindered. So it's not completely happy. And like we said before, whenever you generate this, it very readily undergoes the thermal helix inversion. So a half-life of only 15 seconds, and it generates this stable molecule. And what you can see is because the lower half is symmetric, this molecule bottom right is actually identical to top left. So over the sequence of one photochemical and one thermal step, the upper half has undergone a 180 degrees rotation. And you can keep going. So if you irradiate it again with UV light, it undergoes a photochemical EZ isomerization followed by a thermal helix inversion. And then we've gone 360 all the way around. So during my talk, you'll see in some places these little animations, but they're not just animations. All the thermal steps, so the thermal helix inversion, they're all calculated using computational methods. We've also calculated the photochemical step, but that's not what you see here. They're quite difficult to do, and we've only done that for 2 different cases. So the photochemical step is just an animation in this part. So one synthesis slide, because after that, I'll just show you quite a few examples of molecular motors. But this is important for molecular motors because these are the pivotal pieces of synthesis that you need to know for making a molecular motor. First generation molecular motors are quite straightforward. Using a McMurray reaction, you can couple 2 ketones and react them on to an alkene. It's one of the very few reactions able to actually perform this feat because many of the other alkene forming reactions just can't bring it all the way to an alkene. And we've tried many in our group, and this is one of the very few that actually works. And they're very efficient, but if you want to make an asymmetric molecule, like the second generation molecular motors, you can imagine using a mixture of the different ketones. However, we found out that if you do that, there's a strong preference for homocoupling. And that doesn't give you your desired product, and it's a big mess to get that separated. So there's an ideal reaction for that, which is called the Barton-Kellogg reaction. And for the Barton-Kellogg reaction, you need to convert your ketones into 1 thioketone and 1 diazo species. And these react together in a 1,3-dipolar cyclar addition to give you this intermediate. But this intermediate quickly reacts on. Nitrogen evolves from it, and you get this episulfide. Sometimes we isolate these episulfides, but quite often when we just give it a bit of heat or some phosphorus reagents, they continue on to provide you with the overcrowded alkene, the second generation. So that's for synthesis, and using that, we've made many, many motors over the years. And here are 20 examples of second generation molecular motors with this core structure, where we've only varied the X and Y position using these different atoms. And what I want to show with this is that just by changing those 2 atoms, we can get a whole range of different speeds for the thermal helix inversion step. And that's the step that's quite important in this because the photochemical step is very, very fast, but the thermal step is often the limiting step. And what you can see, I've put this here in bold purple, we have a motor that is so fast that at room temperature, we extrapolated a half-life of just 4.8 nanoseconds. So it's super fast. Whereas another type of motor, this one here, at room temperature, it would have a half-life of 46,000 years, so terribly slow. And then you might think, why would you want such a slow motor? Well, there are quite a few interesting applications, especially involving catalysis, which we'll get to later. But with quite a few other applications, you want them to be super fast because then you can make use of the rotation. Sometimes we like to speak in the temperature at which the half-life is 1 hour. It's something we looked into. I won't go into detail, but it's often more useful since you're working on the same scale instead of on, well, how many is it? 20 orders of magnitude. So this motor, the fastest would only be rotating at a half-life of 1 hour at minus 200 degrees, whereas our slowest motor would be rotating at that same speed at 122 degrees. So with those different speeds, we were interested in what it actually does in solution. So we looked at viscous media. We took this molecule where we added some alkyl chains to make sure that its solubility was good. And we put it into a whole range of alkanes, and we got a really nice correlation with the viscosity over different temperatures. We were able to include that into a modified Eyring equation, and the fit was really good. But when we moved on to using many different solvents, so here you see over 50 solvents plotted, you don't see a nice correlation anymore. So the temperature for this is all the same. It's just different solvents. In the bottom, you see their viscosity plotted, and LNK is the natural log of their rate. And we try to correlate this to different solvent properties, such as polarity and a lot of other things, but nothing fitted better than the viscosity, except we got a slightly better fit for the diffusion coefficient, which makes sense because viscosity and diffusion coefficient are closely tied together. This made us think more about how this molecule behaves when it's in a solvent, and we wanted to know, can it actually swim around or stir a solution? So what we did, we went back to some first generation molecular motors, and we started from this, and then we installed longer and longer rigid arms with one flexible variant as well. And we introduced this into non-viscous and very viscous solvent. And what you then can do is you can determine their dependency on the viscosity. And what we found is that this expressed as the alpha factor is the more viscous the solvent, the more the motor is retarded in its rotation. But it also means that the motor has to displace more solvent while it's rotating around. And this is a relatively slow motor because that's what's suitable for that kind of study. But this prompted us thinking, hey, what if we use a very fast motor, we put it in a solution, and we irradiate it nonstop? Can we see it swimming around? And that's when we got scooped, because this beautiful idea was picked up by another group before we could even do it. And you see that on the right. So I just want to share this with you. It's done by the Tour group in the US. They used one of our super fast molecular motors, and we were planning using NMR. They used confocal microscopy, and they could determine that when they irradiated this motor, its diffusion through a solvent was faster than when it wasn't being irradiated. So beautiful example there. So I hinted at slow motors before. These are these very slow motors, so they're very stable in their metastable state. And we use these to transfer their chirality to other moieties. So on the left, you see a bienol moiety, and on the right, you see a phosphoramidite. And this resulted in 2 publications where we were able to use these as ligands in an asymmetric reaction. So here we have an alkyl zinc addition to benzaldehyde, and on the right-hand side, you see a copper catalyzed 1,4 addition. And the EE you get from it isn't the best EE in the world. So we get a delta EE of 113 and 106, and 106 still is pretty decent. It means that the difference between the 2 EEs that you get, because with the one form we can get the R product and the other form gives us the S product, the difference in EE is 106%. But the beauty in it is that we're able to transfer the chirality from the stereogenic center to the helical backbone to a biphenyl moiety to the copper, and then from the copper onto our reaction product. And I think this is a beautiful example of transferring chirality from one location through a chain to another molecule. There is a much prettier example of this. I've worked later on something like this myself, and I want to share this beautiful publication that came from our group. What they did here is they used this molecular motor, and they doped it into a liquid crystal mixture, 1 weight %. And this liquid crystal is a nematic liquid crystal. Nematic means that it's not chiral, but it does like to organize itself. But when you introduce a chiral molecule, you can induce chirality, making it a cholesteric or a chiral nematic liquid crystal. And on the right-hand side, you can see that expressed by those ripples. Those ripples are actually the pitch in the helix of that phase. And then, to our surprise, what happened is if you irradiate the motor, you change its chirality in that backbone. And that induces a complete change in the liquid crystalline phase. And the surprising feature was that because of a change in surface tension, the whole surface started rotating. And what you see there is what you see there is a glass rod rotating on that surface. And the glass rod is so much bigger. Here you have the volume ratio, so it's trillion times bigger than the molecular motors are. And I think that's beautiful, where you can go from molecular to a macro world change. This is a very cool project where we managed to get a tidally locked rotor rotating. And what tidally locked means is it's like the moon rotates around the Earth. We only see one face of the moon. We never see its other side. And we did a lot of computational studies to figure out what kind of substituents we would need to achieve that in a molecular motor. And in the end, it turned out we needed a methoxy here and a naphtol as the rotating group. So what you see in these calculations is that the naphtol moiety is rotating around the lower fluorine half. But while it's rotating, it's keeping one face of the naphtol facing the fluorine all the time. So what we had to figure out was whether it, during the photochemical EZ isomerization, would keep the same face to the lower half, but then when it did its thermal helix inversion, whether it would flip around, but then maintaining that same face to the lower half. And using a combination of NMR and CD spectroscopy, we could prove that this cycle, it did specifically that. And we could also do it for the other way around. Now you see that the naphtol is sort of trailing the rotation. We could also do it with the naphtol leading it. So this was a very cool project. And yes, it's mainly academic interest, but here we can show some gearing that happens in the molecule. This is an older example from our group. I have not worked on this myself, but this is the Nanocar, and this is, I hope you've seen this before. It's very neat, and again, academically very interesting, because what we have is a molecule with 4 second-generation molecular motors connected to a central chassis that is moving over a surface. It's only doing so not using light, but using the pulse of an STM tip, and it's able to go through a trajectory. And when I saw this, it stood out to me that on the left and right hand side, you see that these second generation molecular motors are mirroring each other. So they're of opposite chirality. And this made me wonder, can we do something with that by combining that? So this has been a big part of my PhD work. And what on the left hand side, you see these 2 second generation molecular motors. We have one of S chirality and one of R, M helicity, P helicity. And then when we merge them together, and that blue core then suddenly has a mirror plane running through it. And because it has a mirror plane, it's not chiral anymore. But on the top, it still has M helicity, and the bottom it has P helicity. So what does that mean? This is an example you might remember if you ever had a chirality stereochemistry class, because it makes that atom here at the bridgehead a pseudoasymmetric carbon atom. And a pseudoasymmetric carbon atom is pretty special. It means that if you would take the mirror image of this molecule, it would remain the same. It's identical. But if you swap 2 substituents, it inverts its chirality. And sure, it's not chiral, but it's a stereo descriptor. And that example you see on the right-hand side. So we have a meso-R structure and a meso-S structure. And because those 2 substituents here, the methyl group and the fluorine, are of different size, these 2 molecules are also of different energy. And meso-R is strongly favored over meso-S. So synthetically, we only obtain meso-R. Then what we do is we irradiate this, and we find that if you irradiate it, only one side, randomly, which side undergoes a photochemical EZ isomerization, giving you these strong helical intermediates. These are not stable, only a half-life of 3 seconds, so they quickly convert back to where they came from. And what we found is that the site that had undergone the photochemical EZ isomerization is also the site that then subsequently undergoes the thermal helix inversion. So once one side starts rotating, it keeps on rotating till it finishes the 180 degrees. And being random which sides rotate, on average, you get both sides rotating. And we hope that these molecules might become the nanocars of the future. So I would like to acknowledge Paul Byrne and Cope for giving me this opportunity to speak to you. And of course, I want to acknowledge Ben Vega and the Vega group for all this fantastic research, and all of my co-workers. I'm not going to name them all, but it was a terrific group of brilliant people to work with. And thank you for your attention.
Very good. Thank you very much. We have time for maybe a couple of quick questions if anyone would like to ask a question. So please, you can unmute yourself and ask some questions. Anyone? No?
So, Jos, what is the furthest distance that someone has managed to achieve driving a molecular motor?
I believe the best our group has done is 20 nanometers. However, it depends on then what you call a molecular motor, because some people call some molecules molecular motor, which I would disagree, because they just drag them with STM tips instead of actually having them drive by themselves. Those people who drag them, they can do hundreds of nanometers, but they're not driving themselves, it's people pulling them.
And what sort of forces can they, sort of, if you work out, sort of the way that they move, what sort of force can they impart on something else? So, for example, can you have a car with a caravan?
I've actually made some of those with a load, and those bits of research haven't resulted in anything yet. So that's still ongoing.
Okay, cool, thanks.
I might ask a very quick question. So you mentioned one of the examples where you were doing the stirring and you were putting longer and longer sort of arms on it. I wonder, is there like how big can it go? Like what are the limits here?
Well, that's actually quite interesting because there is a definite limit. What you get is if you go for longer and longer arms, in the end, we believe that the ends of the arms will just start standing still in the solvent, and then it's just the motor reorientating itself in the middle. So if you go to maximum, you feel like it can move it like this, but in the end, it will just twist in the middle.
I see.
So there is a definite limit. So what has been done, that's not research I was involved in, is these molecules have also been attached to a surface, and then you can go much further because the surface keeps it fixed, and then the arm has to move all the way around. It's a bit like what a flagella does on ATP synthase, and that is much more interesting.
Yeah, I see. All right, thank you. I think for the interest of time, we might have to leave it there. So everyone, as much as we can, a round of applause over a virtual platform. Thank you very much for the quite interesting talk.
Thank you.